Okay, so new topic today, matrices. So we are leaving calculus behind and talking about something completely different today. And what we are talking today are matrices, and we've seen already in our initial formalization of the GLM, which for some reason wants to look like this today. That's not a formula. That's more like a formula. That matrices arise in the theory of the GLM, and the most important matrix that is involved in the GLM is the design matrix. And the matrix language allows to concisely and with very few symbols state a lot of important theory about GLM, and allows to summarize a lot of important statistical procedures in the context of linear models. So it's important. And for one reason or the other, matrices are not that common in school, high school math yet, I guess, although they here and there may occur, like determinants here and there occur. And also in the statistical teaching of psychology undergraduates, I think at least at Freie Universität Berlin, matrices play no role whatsoever, which makes life then unnecessarily complicated. So today we want to cover some aspects of matrix calculus. Sometimes these things are also called linear algebra, but linear algebra is really much more than just matrix calculus. So because it also relates a lot to linear mappings and their relation to the matrix calculus and so on. So we focus here mainly on just talking about matrices as basic units of computations, and want to discuss the following things. So first we want to of course define what a matrix is and how to then create matrices. Then we need to talk about matrix operations, which will be addition, subtraction, scalar multiplication, and matrix multiplication. And once we have introduced those, we will also discuss the inverse of a matrix, and transposition, which will be fairly quick. And I think that's most of the stuff that we want to do today. Maybe we should say some words. We should say some words about determinants and also positive definite matrices, because these things will come up. So we will not, of course, give a full discussion of determinant theory or full discussion of positive definiteness, but we will mention what we need for the GLM. What I came across recently is a book by Searle, which is called Linear Algebra Useful for Statistics. Not linear algebra, matrix algebra, useful for statistics, and that's a really helpful book. I found that's from 1982, because it instead of giving an introduction to linear algebra, where you always have to sift through and then figure out where the matrix calculus that you need for GLM sensor is, this book is fully devoted to that. So that's a really nice book that I came across recently. Yeah, otherwise you find, of course, discussions of all of this, what I'm doing today. You find all of the stuff on Wikipedia anyway. And then there are, of course, on matrices and basic linear algebra, there are many undergraduate textbooks. There's this math for machine learning book that's now out that covers this. So it's really, really standard stuff. And it's actually, if you think about what we did in calculus last week, where things sometimes get a little bit esoterically because you have these limits where you let something go to 0 and so on, this is far less so the case for matrix multiplication, so matrix calculus. So things are really straightforward, and if you can do basic operations on numbers like plus, minus, and multiplication, then yeah, getting warm with matrices is actually not that much of a big deal. Good. So then let's get started with again realizing that OneNote doesn't allow to shift everything out of scope. Something needs to stay on screen. So first, what are matrices? And the answer is matrices are rectangular collections of numbers, and in algebra numbers are of course represented by Roman letters. So a matrix is a rectangular array that then looks in general as follows. In general we use large capital Roman letters to denote matrices. So A is a matrix, and then A has elements, and these elements are then usually written with lowercase Roman letters and are indexed. So a general matrix looks as follows. We have the matrix A here, and this is a rectangular array of numbers, and these individual matrix elements are subscripted according to the row and column index. And here's the already most important thing to get used to. The row column is always first, and the column index is always second. So 1, 1 means first row, first column, that's easy, but 1, 2 means first row, second column, and nothing else. And a 2, 1 means second row, first column, and nothing else. And then the nice thing about matrices is that they always have finite many elements. So at one point you reach the last row of a matrix, which we here call n. So this matrix has n rows, and we already reached the last column here. So you see that this matrix has m columns, and then we have all elements here, and then what you often see is these kind of dots notations. So there are of course elements also between A21 and AN1, but we don't show them, so we put dots there. Oops, wrong dots. These dots. Now matrices also play a role in computing, but one should take some care. Actually, we can here put A2M. One should take some care that you don't confuse mathematical matrices with arrays, or sometimes, at least in MATLAB, also matrices in computer programming. These are different things, and for arrays, like in Python or in MATLAB, the rules that apply to arrays in Python or MATLAB apply, and to matrices in math, the rules of matrices in math apply. That you can represent a mathematical matrix by an array in some computing environment is nice and can help to do calculations, but these are still different things, and one should not think that because there are three-dimensional matrices, for example in MATLAB, that three-dimensional matrices in math exist. They don't. So matrices in math are rectangular arrays with a row dimension and a column dimension, which take this form. Can also be written as follows. So one can also specify a matrix like this, so by specifying the elements and then saying that the subscript of these elements go over n rows and m columns. So that's also a way to write this. To have a very concrete example of this, we can now assume that we have let's say a 4x4 matrix, and we can just put numbers here. So whatever these numbers are. Actually, that's faster to do by hand than what I'm doing now. So I'm a lot quicker to write down a matrix by hand than in this digital way. So that's an example of a matrix with only integer values. In general, we often talk about matrices in a abstract manner, and what we are only interested in actually in the GLM are matrices where the elements are real numbers. So we would state that matrix A is an element in the space of n times m matrices. So that's the notation that we will use throughout. So this you should be able to read. What this says is that A is a matrix, it has n rows and m columns. Yeah, so that's the notation here, and the entries, so the elements of this matrix, are real numbers. So that's quite important. We've seen in a way already special cases of this, because if m equals 1, then of course we have a matrix that comprises a single column. This is then also written as this. So an n-dimensional column vector and a matrix comprising only a single column are the same thing. What is not the same thing is a row vector. So because this notation always refers to column vectors, this thing is just a single row of values. It's a matrix with a single row, but this does not correspond to this, because this is a column vector. This is essential. So an example here would be that we have, or for example, this matrix here, as it has 4 rows and 4 columns. It's also called a square matrix, and it's a 4x4 matrix. Good. So these are matrices. That's how we can define matrices. Other questions about this matrix definition?
I have a question about dimensions of a matrix. Can the dimensions of a matrix be more than 2?
No. In mathematical terms, matrices have two dimensions. They have a row and a column dimension, and that's it. In programming, that might be different. And but that's why I usually call entities in programming arrays and not matrices.
Thanks.
Other questions? No. Good. Now, you should view matrices essentially as the basic unit of computing in real life, basically. So instead of computing with numbers like you're used from school, where you add 2 and 3 and get 5, in real life you add matrices. Hence we want to talk about the operations that can be performed on matrices. So that's our next topic, and we start with addition, subtraction, and scalar multiplication, because they are most straightforward of these. So let's go here. So let's first talk about adding two matrices. So if we have two matrices A and B, we can form a third matrix C as the sum of two matrices. The important thing is these matrices that are being added need to have the same dimensions, otherwise matrix addition and also subtraction is not defined. So if we have two matrices that are both n times m dimensional, then we can form a matrix C so my copying skills need still to adapt to this. A matrix C as the sum of these two matrices, and this sum then also is n times n dimensional and results simply from the element-wise addition of A and B. So let's use maybe the following for A. Always hides itself. So if this is our matrix A, and we have a matrix B that is of the same dimension, so we can just rewrite all of this. Like this. Then our matrix C, which is given by A plus B, or is defined here as A plus B, corresponds to this. So for each we just add all the elements where they are. We don't mix anything around, and get to our matrix C. So there are examples, so I will not, because as you see it takes a little bit of time to write this nicely in this math editor. I will not now give numerical examples. You see numerical examples in the text. It's really straightforward. You have two matrices. They need to have the same size. If they have different sizes, the sum of them is not defined, and you evaluate the sum of two matrices by adding the elements in the specific locations, and that's that. And subtraction is defined in complete analogy. Let's see how this works. So let's assume we have a matrix D, which is given by A minus B. Then we evaluate this by element per element, subtracting the respective elements. Questions about matrix addition and subtraction? Or any remarks on typos that I might have put in? Because that's really easy to put in typos if you have these indices. Okay, it doesn't seem to be the case. That's also fairly straightforward. One more thing that's also straightforward is scalar multiplication. So if we have a matrix A, or let's do it like this. If we have a matrix A and a scalar A, first need to have this. So we still have our matrix A, which is n times n dimensional, and we have a scalar, so just a real number. Then we can define a matrix, let's call that E, A, small a times big A, which is again n times n dimensional, and is evaluated by multiplying each of the elements in the matrix A by the scalar. Maybe it's not that nice if I use A here again, so let's call the scalar B. So, oops, we get this matrix here, and actually you can pre or post multiply a matrix with a scalar because the product here is commutative. This is the same thing. Yeah, so there is also a numerical example in the text, which I will also skip. So that's scalar multiplication, and these things are straightforward. That looks nicer. These things are straightforward because they are element-wise operations. So you don't have to think much. You just apply the operation that you know from school, plus, minus, times, to each element, and you do that for corresponding elements, and that's it. Of course, you can also add matrices that just have a single column. If these two matrices have the same number of rows and the same number of entries, and you would then call this vector addition or vector scalar multiplication if you multiply them, because vectors, as we treated them so far, are just matrices of comprising a single column. So the more important thing, or the thing that requires a little bit more thinking, is the notion of matrix multiplication, and this is the essential thing from this lecture. So this was kind of a warm-up. Matrix multiplication is fundamental for everything that you that we will see, and we will be concerned with it now. So if we have two matrices, A in n times m and B in m times p. And the important thing here is that the first matrix has as many columns as the second matrix has rows. So this these m's here, this is no coincidence that they are that this is both m, but this is necessary for the matrix product to be defined. And these m's are also called the inner dimensions. They need to be identical. If we have two matrices, so n and p can be arbitrary, but this the number of columns of the first matrix and the number of rows of the second matrix need to be identical, then we can evaluate the matrix product of A and B, which is C, which we write as follows. Namely this, just AB. Sometimes you see the dot, but it's actually more common that you don't see anything. So if you see two matrices next to each other, that means this is refers to a matrix product. This is what we of course always see in the GLM for X beta. So this refers to a matrix product. If this is fulfilled, then if these criteria are fulfilled, then we can compute this matrix product, and this matrix product is defined in a specific way. And for that, I think I want to take this thing here. So our first matrix A has these elements, so it has, as we wanted, or as we defined better, it has n rows and m columns. Now we need to write up the second matrix here, which the elements are of course B. And then this matrix has m rows, so it's m times p, and p columns, so this is of course still the same. But here we go up to p. So our right lower corner element is MP. Now, to compute the entries of C, where C will always be an n times p matrix, so the inner dimensions here, these two m's, they disappear, because as we will see, we're summing over B. C is defined as follows. In the upper left corner, so let's maybe get rid of this so that's a little bit easier to see. We write down the sum over the columns of the first matrix and the rows of the second matrix. So if we go for one row over columns, we have m entries here, so A11, A12 up to A1m. If we go down the first column here, we go over B11, B21 to BM1. And in the upper left corner of C, we have the first row. We consider the first row of A and the elements across all columns. And we consider the first column of B. So, and what we do is we multiply the entries and sum them all up. So one way to visualize this is, and what you should get used to is, maybe I can draw on top of it here. So we're going this way and this way. Yeah. So think of that we take these elements, and these elements we then take the A elements, tilt them by 90 degree, overlay them on these elements, multiply all of them. So this is what the sum says, and then sum. Yeah. And this is how we get this first entry here. And maybe let's get rid of this. That's maybe a little bit too fine-grained. The second entry in the first row of C we get by staying in the first row of A, and now considering the second column in B. So we stay with A1I, but we go to B12. And what happened here? Why is my matrix now suddenly smaller? Or it's just the window. It's just the window. And this we do for the entire first row of C, and up to the last entry where we will end up. So we can of course use the first row of A as many times as there are columns in B. So we end up with the pth column of B. So which also already shows that we will have p columns in our matrix C. Now this is how we get our first row of C. The second row of C we now get by going into the second row of A, and then we do the same thing again that we did for the first row. So we again go over the columns of B, but now multiply everything with the elements of the second row of A. And this is also what we will do here, and also what we will do here. And we continue this way over all rows of A, and as there are n rows of A, we will in the end end up with the nth row of A, and hence here have n, and start again with the first column of B, then go to the second column, and end on the pth column. So this is how the matrix product of two matrices is defined, and as you can or as you can infer from this, this is n times p dimensional. So as many rows as are in the first matrix and as many columns as are in the second matrix. I think it doesn't hurt to do a quick example of this. So let's do an example. So let's assume we want to multiply a 2 by 3 matrix with these entries. Let's use small numbers so that we can do the arithmetics. So we have a 2 by 3 matrix. So if we want to form a matrix product, we of course need a matrix with 3 rows, and we can take how many columns we want, but let's say we want 2, so to keep everything at bay here. And let's put this into brackets. And let's assume we have these values. Then the first question is always, now that we have, let's write this down here, now that we have a 2 times 3 times 3 times 2 matrix. The first question is, what's the dimension of the resulting matrix? Interactive part. Somebody please say, what is the dimension of the resulting matrix?
2 times 2.
Yo, thank you. So again, the inner dimensions disappear. If we would have more columns here, this would change. But so we get a 2 times 2 matrix. And so then we can already, which doesn't hurt if you are doing these calculations by hand, already put down that we have 4 entries that we need to take care of. This will again make my thing disappear. So, and then again interactive. What's then the entry here in the left upper left corner? And why? Any guesses?
It's 8.
Is it 8?
10, sorry, 10. My mistake.
Yeah. So why is it 10?
2 multiplied by 1, 1 multiplied by 0, 4 multiplied by 2.
And all of them
Add all
summed
of
up. Yeah. Good. Somebody else? What's the value here? So in the upper right corner.
It's 15, I think.
Yeah, that's also what I think, because it's 2 times 4, so that's 8, plus 3, so 1 times 3, that's 11, plus 4, it's 15. Lower left corner.
15.
And that's 12, that's 15, yep, because we had 3 and plus 12. And here,
26.
let me have a look. 12, 18,
24.
24, right? Yeah. So, yeah. So in principle, this is easy, except for the arithmetics, which one, and of course, everyone gets wrong quite often. Hence, one can of course compute these matrix products in software quite easily. So if you train yourself with matrix products, I also recommend that you actually check, and that's what I always do, check your calculations in a matrix calculator, for example MATLAB. So there's some MATLAB code that shows how to do these operations that we discussed this morning so far in MATLAB. But yeah, so that's matrix multiplication. The question is, of course, why is matrix multiplication interesting? So for now, it's just some kind of somewhat arbitrary way of multiplying and adding up numbers. In math, the magic of matrix multiplication kicks in because you can write every linear transformation, every linear mapping between arbitrary vector spaces. You can translate this into a matrix multiplication. So it's kind of a reference way of computing linear transformations. So that's why matrices beyond pure number crunching are interesting, because you can then, from what you know about matrix calculus, relate this back to linear transformations in arbitrary vector spaces. However, we will not explore that much actually. So for us, matrices are really a way to write models, linear models that we have already seen in the first lecture. So let me remind you of that, that we saw something like this. For p values of beta, and then for I going from 1 to n, we saw this as a basic multiple linear regression model, and the main application for matrices in GLMs is to write n of these kind of equations very succinctly using a matrix formulation, and then being able to develop the inference theory and parameter estimation and testing theory using matrix statements, which of course get rid of always keeping track of all these indices, and also allow for implementing computations on computers much more straightforwardly, because computers can do arrays, so they can do these matrix multiplications fairly well, and then we can easily translate mathematical models into computer code and use standard packages to evaluate expressions. So that's where for us matrix multiplication will be most important. Good. So my suggestion is then to take a break now. Are there questions about matrix multiplication at this point? The thing is, you will not get used to matrix multiplication if you don't practice it. It takes a little bit of time, so take 1 hour and multiply some matrices of small size, so 2 by 3, 4 times 1, 4 by 2, 5 by 2, 3 by 2, whatever matrices, do that a couple of times, then you got it, and then you will also not forget it, but you should be fluent in evaluating this, even if you make arithmetic errors, which are easy to do, but you should be aware of which sum is written in a specific element of a matrix product C. Okay, then let's have a break, and after the break at 10:30 continue with matrix inversion. Good, then let's continue with matrix inversion. And here I will not kind of show you how to invert any kind of matrix, because this is really quite a lot of theory and involves a lot of algorithms like Gaussian elimination and so on. But what I want to give is a motivation for matrix inversion and some notation, and then the inverses of like 1 or 2 matrices that are easily inferred. So the motivation is as follows. So in linear algebra, we might have expressions of this form where A is a n times m matrix, x, because we can form the matrix product is an m dimensional vector, and b sorry, I shouldn't talk crap. We're talking about inversion of matrices. So A is an n times n matrix, so it's a square matrix. X is n dimensional, and B is also n dimensional. Because we're not talking about generalized inverses or pseudo or Penrose inverses, but we're just talking about standard matrix inverses. We have kind of these expressions, and would like to know the value of x while we know the value of a and b. And of course, this kind of setting is fairly familiar if you think of high school calculus, where you dealt with algebraic equations of this form. For example, something like, I don't know, let's say, as an example, 2x equals 6. And the question was always, oops, interesting, question was, what is x? So this is kind of typical high school algebra that you did for some time. It was not really clear why you're doing this, but it was done, and you hopefully remember how you solve these problems. And rather than asking you now for this simple thing, I will remind you of how you did it. What you did is you tried to isolate the unknown, so x is, you call it the unknown, try to isolate this on one side by applying the respective anti-operations. So if you have a multiplication where then the antidote, so to speak, was division, so you would divide both sides, in this case by 2. And if you do that, and you do the same operation on both sides, you get here 2 divided by 2, and 2 divided by 6. 6 divided by 2. And this we can get rid of. And then you can evaluate these fractions, and you get 1x is 3. And from this, because 1x is 1 times x is the same as x, you then get the answer x equals 3. So you basically solved this kind of algebraic equation here for the unknown by applying the anti-operation to multiplication and solve for x. And matrix multiplication, matrix inversion can be motivated exactly in the same way. So if you assume in such a matrix statement, you know the entries of the n times n, so the square matrix A, and you know the entries of B, and you want to know x. So you want to solve this system of linear equation. This is also what this is called. You want to solve this for x. You need to somehow apply this anti-operation of matrix multiplication. And this anti-operation of matrix multiplication is called matrix inversion. And the notation then is exactly as you're familiar with from this approach here. So maybe let's start here. When we say we want to divide by both sides by 2, this is obviously the same as multiply both sides by 1 over 2. So if we write this in an abstract way, if we go from here to here, oops, then we actually multiply by a to the power of -1. Do that on both sides so that the equality does not change. And then we have here the fact that if we divide a by a, we get what is called the neutral element with respect to multiplication, namely 1. And on the other side we still have our a to the power of -1b, and from this then derive that x is a to the power of -1b. So let's make this nice. So this is just restating again what we've seen in terms of numbers, stating this again in algebraic terms. Now with matrices we can basically follow exactly the same logic. We can starting from such a statement, we can multiply both sides by what is known as the multiplicative inverse of a matrix, and which we denote by a to the power of -1. And like for matrix multiplication, although I didn't make this explicit, matrix multiplication is not commutative. So if you have an n by m matrix and you multiply this by a m times p matrix, that's fine. But if you reverse the order of the matrices, then you're multiplying an n times p, or you want to multiply an n times an m times p matrix with an n times m matrix, and the inner dimensions don't are not the same, so this doesn't work, and hence we of course always need to be aware of from which side we multiply a matrix. So here we multiply on the left side of this, and this then in matrix terms yields the neutral element with respect to multiplication in matrix terms, which is the identity matrix. And the identity matrix is written like this. I'll tell you in a second what that is. And the identity matrix has the same effect as the one has in standard multiplication, namely if you multiply any matrix by the identity matrix, as long as it's defined, nothing changes. So in times x gives you x, and then we have solved for x, namely x is the inverse of a times b. Now what's the identity matrix? The identity matrix is just n times n that's n times n matrix with all 0 elements except for on the diagonal where it's 1. So it looks like this. Let's take one of our matrices here. So we have on the diagonal we have 1s. It's not an it's a square matrix, so we have n rows and n columns. And it looks like this. Oops, sorry. Well, one can write it like this, but maybe it's more explicit to write it like this. Now if you think of forming the matrix product of an n times whatever matrix with this matrix, what you do is you multiply each element in the second matrix with this 1, and each element, all other elements in this second matrix by zeros, and then you sum it all up, so you remain with the original element. So multiplication with the n-dimensional identity matrix doesn't change anything. So that's the neutral element with respect to multiplication. So the inverse of a, and this then leads to the definition of the inverse of a matrix. So inverse of a square matrix, and we're only talking about square matrix, and we are actually only, and this is also important, we're only talking about invertible matrices. So there are matrices for which these inverses exist, but there are also many matrices for which they don't exist. And if it exists, is the matrix A to the power of -1 such that if existent, such that A -1 times A equals the n-dimensional identity matrix. And actually one feature of the inverse matrix is that it doesn't matter actually on which side you multiply it, but that's a feature here of this specific case. Of course, if both of them are n by n matrices, you can clearly multiply them either way. And the inverse gives the identity matrix if you multiply from the left or from the right. So that's the inverse of a matrix. Easy example for inverse matrices, and one that we will also have see later on, are matrices that are diagonal. So if we assume we have a matrix like this, which is called a diagonal matrix. Diagonal matrices are matrices that only have non-zero elements on the diagonal, on the leading diagonal, but in terms of n by n matrices, the diagonal is just the diagonal. The inverse matrices of these are given as follows. So if D is a diagonal matrix, then, so maybe we write it like this. So this is how you can in general write diagonal matrices. So this D1 to Dn are the diagonal elements, and Diag says you should put it on the diagonal and everything else is 0. The inverse of such a matrix in general is the diagonal matrix that has on its main diagonal the inverses of the diagonal elements. So in this case D -1 would be 1/10, oops, and 1/8. It's actually nicer if we don't do this. So, and that this is actually the inverse we can check by forming the matrix product. So if we do D -1 times D, we get 10, 0, 0, 8 times this. And now we need to form the matrix product, and we get 10 times 1/10, that's 1. And here these zeros, they yield 0, so we get 1 here. So we get a 1 here. Then we get 0, and so 10 times 0 and 0 times 1/8, that's 0. And we get here we get 0 times 1/10, that's 0, and 8 times 0, so we again get a diagonal matrix. And here in the end we get 0 times 0 plus 8 divided by 8, and that's 1. So we get the diagonal matrix, the identity matrix. And hence we have shown that no, we haven't shown anything. We've just calculated an example that this actually holds. However, oops, what was that? In general, to compute inverse matrices, yeah, it can be done in using different kind of algorithms. There is an example algorithm that is useful when doing things by hand for small matrices in the script. So this is this Gaussian elimination part where you basically write the identity matrix next to the matrix of interest, and then you use elementary operations like exchanging rows, multiplying a row by a number, and adding and subtracting rows to get the matrix of interest to the identity matrix, and apply the same thing to everything that you write next to it. And then what you have next to it is the inverse. And this you can have a look at. This is nice, so it helps to, in a way, understand a little bit what inverses of matrices are. There are, of course, if you go into numerical mathematics, there are other and sometimes better algorithms that achieve a similar thing. In the end, if you implement something in numerical computing, you will use some kind of package to do matrix inversion, and you will not do it by hand. So these kind of algorithms, I think so when I did my linear algebra courses, of course considerable time is spent on computing normal forms of matrices like pivot forms and or drawn normal forms, and also computing matrix inverters and so on. That's all good for understanding, but after that's a little bit like often in your studies, it's not of that much practical use if for actual numerical computation. Sometimes inverting matrices is also necessary for in theory. So if you build computational models, and sometimes it doesn't hurt to know how to invert a matrix, and then the theory helps. But in general, one does this by means of a computer, and of course you can do that in MATLAB, and then you get the inverse. The important thing is that you remember that the inverse, if it exists, and as I said, there are many matrices that don't have inverses. So for example, if you think of the 2x2 matrix, let's briefly have a look at a non-invertible matrix. So if you have this matrix, then whatever you any n by n matrix that you multiply by it will never give the identity matrix. So this matrix is clearly not invertible. If it exists, and there are ways to check that it exists, which we will not go deep into, then it's the matrix that, if multiplied with the matrix that you're trying to invert, yields the n-dimensional identity matrix. Okay, so I think this is what I want to say about matrix inversion. Are there any questions about matrix inversion?
I have a question. We only looked at square matrices, but does this imply that non-square matrices cannot have an inverse, or not?
Yes. Yeah. So that's a good point. The term inverse of a matrix applies only to square matrices and non-square matrices. So matrices that we've seen already up here don't have an inverse. They can have something that's called pseudo-inverse, and this is actually something that we will see. So one can generalize this notion of a matrix inverse. The question is what that then is, because clearly the identity matrix is a square matrix, and if you have a rectangular matrix with let's say ones on the leading diagonal, you still have some columns with only zeros here, which is then not an identity matrix. So yes, so that's important. Actually, the whole theory of matrix inversion and invertible matrices and determinants, which are used to check the inverses of whether a matrix have an inverse, only apply to square matrices. Yeah. And I think actually Penrose. So because I mentioned, so you have this generalized inverses of matrices, for example the Moore-Penrose matrix, and I think this Penrose guy is the same guy who just got the Nobel Prize something in economics, as far as I could tell from what I googled together. But again, matrix inverses only exist for square matrices. Any other questions? Good. Then there are three little things that we will also need because they show up in formulas and yeah, are kind of something that we need in our GLM theory. And the next thing that we have is transposition, which is also a matrix operation. Now, transposition is just a reordering of the elements of a matrix. That's essentially swapping rows and columns of a matrix. So if we have a matrix A, we are now again can talk about this for all matrices, not only square matrices. If we have an n times m matrix, then the transpose of A is denoted by a t. Sometimes you also see a prime. I like the t more so that we don't confuse this with derivatives, which one can also talk about, but that's a completely different topic. So that's why I'm using the t for transpose. That's then m times n matrix, and what happens there is that we put the elements that comprise the first row of A into the first column of the transpose of A. So let's maybe use this here because then we can see it for more than one row. So if our A is this is A, then the transpose of A, let's do a little arrow here, has in its first row the elements in the first column of A, or, and that's equivalent, has in its first column the elements of the first row of A. So maybe let's start with let's go over columns in AT. So we put the elements of the first row of A into the first column. So this remains the same. So the diagonal or the leading diagonal elements are not swapped. Yeah. But then here we have 1, 2, so we take this element and we continue to 1m. So we clearly now have m rows. We take the second row and put it into the second column, so we have 2, 1 here, 2, 2 remains the same, and we go up to 2m. And so we continue with here the rows, and in the end have here n1. So we have n columns, n2, and this element also remains there. Yeah. So that's essentially transposition, which shows up in formulas. It's exchanging the row and column dimension essentially, if you want. If one thing that is maybe of interest, if you have some vector x and you transpose that, then you get 1 times n matrix. And if you have a scalar, which is often happening in some calculations, then the transpose of this is the same scalar. So nothing happens if you transpose a scalar. It just remains the same. If you transpose a vector, if you get from a column vector to a row vector, or if you transpose a row vector, you get to a column vector. Okay, questions about transposition?
Yeah, so can I just confirm that the top left and the bottom right element would remain the same in both? So A11 and ANM is indeed the same in both matrices, correct?
Yes, but it's so yes, but of course, if you refer to the elements here, this is the nth element. So look at an example. For example, in the script, there's an example of a matrix. Well, let's write it down. So let's take this here, and if we, oops. If we look at this and transpose this, then obviously we get a 3 by 2 matrix, right? And we get 2, 1, 4 and 3, 3, 2, 6. So indeed the lower right element here and the lower right element here and the upper left element here and the upper left element here are identical, but they of course are in a different layout.
Yeah, right. Okay, thank you.
Good. Other questions? Okay, then very briefly about determinants. So determinants are something that we only will see in the multivariate Gaussian distribution and or PDF, I should say, in the PDF. So the probability density function of a multivariate Gaussian. There it shows up, so it doesn't hurt to have revised the term so that you know what your Gaussian PDF is about. In general, there's a long theory and long history of determinants, which we will basically not really go into. So determinants can be used to check whether systems of linear equations have infinitely many solutions, no solution, or a solution. So this refers to the fact of whether square matrices are invertible or not. And one can also, if one goes to vector spaces, one can understand determinants as the volume of the spaces that are spanned by the columns of a matrix. That's all very interesting, but we will actually not do much with that. So I will just remind you of two specific determinants. So just to remind you that you have seen determinants before, I assume, because they are for I'm just looking for this here, for 2 by 2 matrices and for 3 by 3 matrices. You might have actually calculated determinants before. One important thing about determinants is that they are scalar numbers. So if you have a matrix, a 2 by 2 matrix here, then the determinant of this matrix is a scalar, and this holds for any kind of matrix. So it's always a kind of a scalar measure of essentially the volume of the column space of this matrix. The determinants determinants are written with these two vertical bars. Actually, it would be nicer to have these bars a little bit larger. Let's see what happens here. Yeah, that's more like it. So this is how a determinant of a 2 by 2 matrix is denoted and is evaluated, and this is maybe something you remember from school, by multiplying the diagonal elements and then subtracting it from one another. So you multiply this way and you multiply it this way, and you subtract what you get from one another. So if I go back here, get rid of this. What you get from this is A11 times A22 minus A12 A21, and then a basic check for whether a matrix is invertible is whether the determinant is 0 or not. So if it's not 0, then it's invertible, and this, if we would discuss eigenvectors, that would be something that would be interesting. So if you go to the machine learning course from last summer term and you look at principal component analysis, their determinants play a more important role because they are a key factor to figure out what the eigenvectors are in terms of the characteristic eigenvalues and eigenvectors of a matrix are in terms of the characteristic polynomial. However, we will not need this. I just want to bring up the determinant term, and that because we will have in the Gaussian PDF, we have the determinant of a matrix in there, which will look like this. And I want to remind you that at least for 2 by 2 matrices, you actually know how to evaluate the determinant, and you also know that it's just a number. For 3 by 3 matrices, it's a little bit more exciting. Where do we have a 3 by 3 matrix here? If we have a 3 by 3 matrix, there is what is called a Sarus rule to compute the determinant of that. In general, there's of course also a general definition of determinants. I think that's called Leibniz formula, as far as I remember right now. But to introduce this, you need permutation groups and stuff, and that's really we would spend way too much time in elementary math. So if you are interested in the general definition of a determinant, have a look at Wikipedia, and be aware that you will need to spend considerable time on that if you are happy with evaluating the determinants of 2 by 2 and 3 by 3 matrices. That was awesome. Then what we are doing here is enough. Why? Thought I copied that. So Sarus rule is a way to compute determinants of 3 by 3 matrices, and what you have to do for Sarus rule to work is that you, in your head, you have to write the first 2 columns next to it. Oh, that's good. That's the first time that this small thing here helps. So you write something like this next to it, and then you compute products in both ways. Where are we here? So you compute this product, you compute this product, and you compute this product, and these are positive terms in the determinant, and then you compute this product, and this product, so the product of these elements, and these are negative terms, and these then yield the determinant. So the determinant here evaluates to no, it doesn't let me click on it. What's going on now? Am I pushing it too hard? Oh, now it lets me click on it again. So the determinant here is A11, A22, A33. That's one of the positive terms, plus A12, A23, and then A31, plus A13, A21, A32, and then the negative terms are A12, A21, A33, next negative is A11, so A11, A23, 23, and A32, and the last negative term is the opposite, the other diagonal, the diagonal the other way around, like this. Let's briefly check. That looks good. 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 And that looks good. So if I have typos, at least I have the same typos here on screen as I have in the script. So these are how you can compute determinants of 2 by 2 and 3 by 3 matrices. One last matrix type is also interesting, namely diagonal matrices. So the determinant of a diagonal matrix, because all of the off-diagonal elements are obviously 0. If you kind of intuitively generalize what we did here, although that's not really how it works, the determinant of a diagonal matrix just corresponds to the product of the diagonal elements, and this is something which we will actually need when we talk about spherical covariance matrices. So the determinant of this is just the product of the elements. Yeah, so if we have a diagonal matrix with diagonal elements d1 to dn, then the determinant of this matrix is the product of the diagonal elements. So this is what I want to say about determinants. Again, I'm just scratching a little bit the surface and basically just mentioning what things that we will need later on. This is not a development of the meaning of determinants or the use of determinants or general definitions of determinants. It's just something to remind you that you may have seen something like this before. You can also use these kind of Saurus rule things to compute the solutions for linear systems of linear equation. That's something that you might have done in school. At least that's what I used that for in school, to compute solutions of these kind of things based on determinants. Yeah, that's everything that we need about determinants. Questions about that? But only what is on screen, not determinants in general. Okay, that was also not a fair question opportunity. Good. So then the last thing is the notion of symmetric and positive definite matrices. This again relates very much to the probability density function of the multivariate Gaussian, because there we will require the covariance matrix parameter, which would be the sigma. We require that to be positive definite, and this will be just a requirement. And positive definite matrices are also not that straightforward. So the definition is somewhat straightforward, but is also fairly general, so that in principle we would check a lot of things to check whether a matrix is positive definite. The other thing is then that it's not really easy to appreciate, but nevertheless I want to mention it here so that I can in some in some way at least say that certain matrices are positive definite. So first, symmetric matrix, that's straightforward. So if we have a matrix R that is square, so R is symmetric if the transpose of A equals A. So if we swap around the column and row ordering of A, then nothing changes. So let's have a look at a simple case here. So a 2 by 2 matrix. If we have a matrix like this, the important thing is that the kind of mirror symmetric elements are identical. So if we, for example, have a matrix like this, this is symmetric because transposition doesn't affect the diagonal elements. And so we're only talking about square matrices here again, of course. It doesn't affect the diagonal elements. And then if we put the first row into the first column, because these elements, so the off-diagonal elements are identical anyway, we get the same thing. So if this holds, so if these off-diagonal elements are identical, then it's called symmetric. Maybe let's do one more so that you see that also for 3 by 3 matrices. So if we have something like this, so this needs to be the same already. On the diagonal we can have whatever we want, but if we, for example, here have a 6, then we need a 6 here as well, and this will be put here. So this needs to be here as well. So you see that we have 2, 3, 6 here on these off-diagonal elements, and here 2, 3, 6 as well. If we transpose this, then if we now put the first column into the first row here, or we put the first row into the first column, nothing changes. So these are symmetric matrices. And positive definite matrices are always symmetric, but they fulfill a more general criterion, namely the criterion that if they are multiplied by a vector, actually this is actually positive definite. There's also positive semi-definite. That would be if we have the larger or equal thing here. If this holds, A again is a square matrix, so let's put this in here. If this holds for all real vectors. And this is of course quite a strong criterion in the sense that to figure out, based on this, to figure out whether a matrix is positive definite, you would have to test for a given matrix, you would have to test all possible n-dimensional vectors and to check whether this, which is sometimes also called sandwich product, is larger than 0. Note here that this is actually a scalar, so you have, just to make this clear, you have x is n-dimensional, so maybe let's put this below this. So x is n times 1 dimensional, so the transpose is 1 times n. And then we multiply that by a, which is n times n. And then we multiply that by n times 1, which is x. So if we look at the dimensions here, if we maybe do the first product first, then we get rid of the inner dimensions here, so we get to a 1 times n matrix, and if we then do the second product, the inner dimensions go away again, and we get to a 1 times 1 matrix, which is just a scalar. So these kind of expressions, so kind of a square of a vector and sandwiched between it a matrix, a square matrix, always evaluate to scalars. However, we would have to test that for all possible real vectors, and this, of course, would be a lot of work. Of course, there are other criteria based on which one can figure out whether a matrix is positive definite. There is an example in the script that proves for a 2x2 matrix that it's positive definite based on figuring out what happens if you actually multiply it with vectors, and that this always needs to be positive. So for a non-zero vector, actually, yeah, so that's something that I forgot here. You need to test it for all but for the zero vector. So if you multiply the zero vector, then it's allowed to be 0, but the zero vector is excluded here. So that's the general definition of a positive definite matrix. If you want to figure out for matrices whether they are positive definite or not, there are other criteria you can use, but you would have to study them on your own. Yeah, so I think that's what I want to say about positive definite matrices. Are there questions about this? Again, this is just scratching the surface and giving you the definition of symmetry and positive definiteness without now being able to evaluate for each matrix whether it actually, or whether it's symmetric. You can evaluate, you just need to look at its transpose, but whether it's positive definite, yeah, you will not be able to figure out based on this. Any questions though? Okay, doesn't seem to be the case. So, yeah?
Regarding determinants, actually, not positive definite matrices, but I've been wondering why non-square matrices have determinants. I mean, why only square matrices have determinants?
Well, the determinants are defined for square matrices. And that's about it. Of course, you can define some generalized concept of determinants for non-square matrices, but the mathematical determinants that we are interested in and that will show up, namely in the PDF of a Gaussian, apply to square matrices. That's just how that is. So, not a very exciting answer. Okay, good. So these are the key things in terms of matrix algebra that we will need. Again, there is this book by Searle on matrix algebra useful for statistics. Maybe I briefly show it to you. So that's oops, it's disappearing because it's not a face. This is a very nice book which goes over the basic operations as well. Well, this you cannot see. Discusses special matrices like symmetric matrices, quadratic forms, determinants, inverse matrices, and then also, which is actually an important topic in the GLM, which we will only also scratch upon, the notion of rank. Solving linear equations, and that's about it. So that's really a really nice book. It avoids discussing many concepts of linear algebra that you would see in introductions to linear algebra. But I can also only recommend that every one of you does a course in linear algebra if you want to do science. And there are some references that come with the script. For example, the book by Gilbert Strang, who also has a lot of online tutorials, or let's say lectures, on linear algebra. So get into linear algebra and matrix calculus if you want to do science. Good. So with this, I would then stop for today, and then we continue today at 3 p.m. with some EG stuff, and next week we continue with, I think it's already probability theory then. So for the scan people, I highly recommend that for the probability aspects, that you also have a look at the statistics for data science, probability spaces and random variables, and maybe even multivariate distributions, because there's a lot of overlap. So in we will not spend that much time on probability theory because we will need to get to the GLM soonish, but hence we will, like we did in calculus, go over things relatively quickly. If you want to spend more time with probabilistic concepts, these early lectures of statistics for data science really are devoted to only that. So I would recommend actually for next week's lecture, which will review, let me just check, which will review probability theory as far as I remember. Yeah, it will review probability and random variables, that you go over the videos in statistics for data science on probability spaces and random variables already, so that you are aware of what's coming up. Of course, this is also all written up in the script, but if you have never seen random variables in your life, that's something. Good. Then let's meet again at 3 p.m. Bye bye.